Sir, your screen is yet to be seen, sir.
Is what?
Yeah, it is about to be presented. Just a minute, sir.
Can you see it? Is it clear? A window.
Actually, you can just click the present now, and you can just click your entire screen so that your entire. I'm just finding, sir. Yeah, now it's fine, sir. Now it's fine. You can proceed, Professor.
You see it clearly? Okay.
Yes, Professor. It's fine. You can continue.
Okay, thank you. Okay, this talk will be on, which is better, this way maybe? Oh, sorry. I think, yeah. Yeah. Okay. All right. So this is a talk about one absorbing primary ideal. And so what is this all about? One absorbing primary ideal of commutative rings. Okay, let me start by saying that this talk rely on two papers with my co-author Age Yetkin. She's a Turkish mathematician. We end up writing these two papers recent. One of them, I think it's already appeared, 2020, and the second one get accepted. If you are, of course, in this talk here, I will just summarize or, tell you what is this about. If you are interested in these two papers, they are available free download from my personal webpage. And you see it down here, my personal webpage. Okay? All right. If there is a problem, please stop me. Is it very clear or not yet? Or I make it bigger?
Professor, the screen is fine. Voice is breaking a bit. Professor.
How is that? Is that better?
Yes, Professor. It's fine. You can proceed, Professor.
Is it good now?
Yeah, now it's fine, sir. Now both you're audible as well as the screen is also clear now. You can continue, sir.
Okay. So we'll do that. Okay. So I continue. I continue with some history. Throughout this talk, rings will be always commutative. And I start by reminding you with some definition that I need for this talk. One of the definition, what we mean with a quasi-local ring. If you have a commutative ring and the ring has only one maximal ideal, then we call it quasi-local ring. If you read from other books, some books, they call it only local ring. But here I will call it quasi-local ring, okay? And you need that in order to continue with my talk. You need this concept. You need to know what I mean with the quasi-local. It means commutative ring with exactly one maximal ideal. And if you have a proper ideal, what I mean with the radical of I, radical of I, as all of you know, but I remind you, are the elements in R in the ring where R to the n is in I for some positive integer n bigger or equal to 1. So that means I, as an ideal, live inside the radical of I, because you can always let n to be 1, right? And definitely all the elements I are in the radical of I. So using street language, what I mean with the radical of I, uh, I mean exactly uh, what I told you. I mean all the elements in the ring where R to the n is in I for some integer n. Okay, in 2007, Badawi, and that's me, we generalized the concept of a prime ideal to something called two absorbing ideal. Okay, what do we mean with the prime ideal? As all of you know, prime ideal means whenever you have a product of two elements in the ring, if you have two elements A and B in R, and A B in I, then A in I or B in I. Okay, so the concept of a prime ideal rely on a product of two elements in the ideal I. Two absorbing mean rely on the product of three elements in I. So if you have an ideal I, we call it two absorbing ideal. If whenever you have three things in R and A, B, C in I, then A, B in I, or A, C in I, or B, C in I. Okay? That's exactly the definition of two absorbing ideal. So if you look at the definition of two absorbing ideal, what we call it the prime ideal, you can call it now one absorbing. Why one absorbing? Because remember the definition of prime has to do a product of two things in I, and you need one of them to be in I. Here, two absorbing, meaning I have three things, product of three things in I, and I'm asking that a product of two to stay in I. Okay? Still with history, in 2013, we introduced weekly to absorbing. What is the definition of weekly to absorbing? We only added one extra condition. Remember, for two absorbing, we ask whenever you have a product of three things in I, then I want a product of two of these three to stay in I. Here we add, I want the product in I, and I add one more condition that ABC is not zero. Then a product of two things stay in I. So the definition between the difference between weekly and without weekly is this thing here, ABC not equal zero. I add this condition if I talk about weekly. Okay, and as you expect, my colleague David Anderson and I in 2011 we generalized to absorbing for n absorbing in general for any n. And what does that mean? Remember the definition of two absorbing. Whenever you have a product of three things in I, then a product of two should stay in I. So in absorbing mean like whenever you have a product of n plus one element in I, then you want a product of n of these elements to stay in I, as it's mentioned here. Okay? So we have so far, we need to know what we mean with two absorbing and weakly two absorbing. And this concept here, I will not use it in this talk for any n. Anyway. Okay, and then in 2014, myself and Ticker and Yetkin, my co-author, the one I told you earlier, we introduced two absorbing primary. What do I mean with two absorbing primary? It means whenever you have three things in I, A, B, C in I, then I want AB in I, or AC in the radical of I, or BC in the radical of I. Okay? Whenever I have a product of three things in I, then I want this condition or this condition or this condition. Okay? Again, what do I mean with weakly? Weakly, I just add one more condition. As I told you, I still need ABC in I, but I ask for ABC not to be 0. When I add the ABC not equal 0, then we mean with weakly. Okay? So we have, and remember again, what is the radical of I? Radical of I are all the elements in R where, let's call it R, where R to the N is in I for some N. So to follow my talk, you need to know what I mean with two absorbing maybe, radical, and you need to know what I mean with the quasi-local. Again, quasi-local means a commutative ring with exactly one maximal ideal. Okay, so now we go to the talk for today. What do I mean with one absorbing primary? One absorbing primary, it means this. If you have a proper ideal, we call it one absorbing primary if whenever, and please look, pay attention to that, not any ABC. If whenever non-unit element ABC, what do I mean non-unit? I think all of you know non-unit mean not invertible under multiplication. Okay? Whenever you select three non-unit element in R and ABC in I, then I want AB in I or C in the radical of I. Okay? That's the definition of um, one absorbing primary. So one absorbing primary, read it carefully, not whenever you have a product of three things in I, then A, B in I or C. No, the three things you need to select, they have to be non-unit, meaning non-invertible elements that are not invertible. And if the product of these three things in I, then I want AB in I or C in the radical of I. Okay, and let me remind you what I mean with a primary ideal. Primary ideal mean whenever I have AB in R and AB in I, then A in I or B in the radical of I. And here AB can be anything. Whenever you have a product of two things in I, then A in I or B in the radical of I. That's the definition of a primary, where the definition of one absorbing primary, the three things we're going to select, they have to be non-unit. And when I multiply them and I get an I, then I need A, B in I or C in the radical. Okay, here is something you could observe, that primary always give you one absorbing primary, and one absorbing will always give you two absorbing primary. So these primary, one absorbing and one absorbing, the new term, one absorbing primary, will mean two absorbing primary. Okay, and you're gonna see maybe in this talk that you cannot go in reverse. Okay, all right. I'm sorry, I keep is everything okay? Can you hear me?
Yes, Professor, it's going fine.
Okay, thank you. All right. So let me start by giving you some properties of primary one absorbing primary. Okay, the first one I just told you, whenever you have a primary ideal, then definitely we're going to have one absorbing primary. So you're going to tell me, what about the converse? Can you give me an example of one primary that is not primary? Here is the example. You take the ring A to be the polynomial ring with two variables and K to be a field. And you take this ideal generated by XY, and you do the localizing. You localize A at M. All of you familiar with this from abstract algebra. Then definitely my R will be quasi-local when I localize at this maximal ideal. Okay? Then this ideal, you need to check that, or maybe you will rely on a theorem that I will mention later on. If you take the ideal generated by x squared and xy, this ideal will be absorbing ideal of R. Remember that R is A localized at M. Okay? Yeah? Anything wrong?
No, Professor, no, you can carry on.
Okay, thank you. Then the radical of I will be XR. However, this ideal, x squared comma xy, R is not a primary ideal. So we do have an example of one primary, one absorbing primary that is not primary. What about the second? Because remember I told you, if I is one absorbing, then I is two absorbing. Remember what I mean with two absorbing primary. Two absorbing primary mean whenever you have ABC in I, then you want AB in I or AC in the radical of I or BC in the radical of I. One absorbing always mean two absorbing primary. So can you give me an example of two absorbing that is not one absorbing? And the answer to the question is yes. And you see number 4. Number 4 is an example of, how can I get rid of this? Go. Okay. This bar here, I don't know. I'm trying to get rid of it. Yeah, here we go. If you take your rank to be the integers and you consider the ideal 12R, I mean, you remember R is the set of all integer, then I will be two absorbing primary. However, it is not one absorbing primary. You can check that the ideal generated by 12 and my rank is the integers. Then this ideal will be two absorbing primary, but it will not be one absorbing primary. Okay. So what are the properties of one absorbing primary? That's the question we need. Well, the first absorbing primary will be prime ideal. In fact, for me, this is the most beautiful result that I never thought it will be correct. Let's read it. The first result, theorem. If you have R and R has one absorbing primary that is not primary, then R must be quasi-local ring. Wow. If you think about it, just chill out and relax and read that carefully. This is kind of, for me, I mean, everything is personal. This is a very amazing result for me. That if you have a ring and the ring has one absorbing primary that is not primary, then the ring has to be quasi-local. And remember what quasi-local mean? It means a ring with exactly one maximal ideal. Okay? Well, so let's stop for a minute. That means if you have a ring that is not quasi-local, then there is no difference between one absorbing primary and primary. The two definitions are equivalent. Okay, that's what you conclude from this result. If your ring is not quasi-local, then the two definitions are equivalent. What are the two definitions? One absorbing primary or a primary. There is no difference between these two. One of them imply the other, and the other imply the first. Okay? And this is, I think, what I wrote here. So if your ring is a product of two rings, then definitely your ring R will not be quasi-local. Then an ideal in R will be one absorbing if and only if I is a primary ideal. Okay. And if you come up with this result, like if you have a product of two, then can you please tell me how the one absorbing primary look like? Well, I just told you that in this case, the one absorbing primary, they are nothing but primary. So that's exactly what this result tell you. Okay, the next thing I'm gonna tell you, you're gonna ask me a question. How do you construct one absorbing primary that are not primary? That should be a good question. we need to know how to construct one absorbing primary that are not primary. Okay? And of course, from the previous result, from the previous here, in order to do that, my ring should be quasi-local. Because if my ring is not quasi-local, then one absorbing primary will be nothing but primary. Okay, so I remind you with some definition here. What I mean with a non-zero element, we call it irreducible. If whenever you write X as a product of two things, then one of them has to be a unit. Unit mean invertible element. And also we recall what we mean with the prime, that if X is a factor of a product of two, then X has to be a factor of the first, or X has to be a factor of the second. Okay? Okay, in a quasi-local ring, this I mention here lemma. Why? Because I need it in the proof of what I'm gonna tell you next. And this is kind of also nice that if your ring quasi-local, meaning if your ring has only one maximal ideal, then every prime element is irreducible. So there will be a prime element, meaning if X is a factor of X1, X2, then X has to be a factor of X1, or X is a factor of X2. Where irreducible, whenever you write X as a product of two things, then one of them has to be a unit. And remember, by definition, prime and irreducible, we already assume that X is non-unit. So if your element is invertible, then we do not use irreducible or prime. To talk about irreducible and prime, we assume that my element is not invertible. Okay, here is how you start with a quasi-local ring, and there are many of them, with maximal ideal M. And you select X to be in M. M is the maximal ideal of R. Okay? And M, assume M, the maximal ideal, is not equal to XR. I mean, M is not the principal ideal ring. Ideal is not a principal ideal. M is not generated by one element. And X, I selected X to be in M. Then XM is one absorbing that is not the primary ideal. Okay? So this is how you construct, and to come up with the quasi-local, just choose your favorite integral domain, and then choose a prime ideal and localize R at the prime ideal. Then definitely this will be quasi-local, and then follow the steps. And that's exactly what I did here. In the example I just gave you earlier, that's what exactly I did. I selected my A to be the polynomial ring, where K is a field and M is the ideal generated by XY, and you take R to be A localized at M, then R will be quasi-local. Then I took this ideal, if you notice I, the maximal ideal is this one, M index M. And I took this maximal ideal and I multiply it with X. You see what the theorem tell me? Choose an X in the maximal ideal, and then XM is one up. So this one here is one up. So this is how, in fact, you construct one absorbing primary that are not primary. Okay? All right. And here are more properties of one absorbing. Okay, what does this tell me? If you have an irreducible element in R, suppose I is one absorbing that is not primary. Okay, so that means I know where I live. That means my ring has to be quasi-local. What can I conclude about the ring? There must exist an irreducible element and a non-unit y where xy in I, but neither x in I nor y in the radical of I. Furthermore, if AB in I for some non-unit elements AB such that neither A in I nor B in the radical, then A must be an irreducible element of R. Okay, so I mean, in the street language, what this theorem tell me? Tell me if I have a quasi-local ring. Why quasi-local ring? Because I have one absorbing, I is one absorbing that is not one absorbing primary that is not primary. So definitely that tell me my ring is a quasi-local. Okay, if this is the case, then I get some information about this ring. It must contain an irreducible element. We call it X. Remember what irreducible mean? That if X, you write X as a product of two things, then one of these two things has to be invertible element or unit. And another element y where xy in I, but neither x in I nor y in the radical. And another thing I know, if AB in I, AB are not unit, not unit, non-unit, and neither A in I nor B in the radical of I, then A has to be irreducible. Okay, here is another way to construct one absorbing. But here you have to be careful. This construction will always give you one absorbing, but I cannot guarantee that it is not a primary. So in the next theorem here, let R be a quasi-local ring with maximal ideal M and P be a prime ideal where B lives inside. Then PM is one absorbing primary. Okay? PM is always one absorbing primary. Okay. Okay, so the question is then, here is the question you're going to ask me. If you have a ring, a quasi-local, yeah? Is it okay?
Sir, it's okay, sir. You can proceed.
Okay, thank you. Here is the question you might ask me. You might tell me like in a quasi-local, is it like one absorbing primary are different from a primary? Well, not always. Okay, because remember that if we have one absorbing primary, then it has to be that is not a primary, then the rank has to be quasi-local. So the question you're going to ask me, what about if I have a quasi-local? Does one absorbing primary mean primary? No. Why? Here's some examples. First thing, I need to remind you what I mean with divided prime ideal. Divided prime ideal, like if you have P is a prime ideal. So what do I mean with P to be divided? It means if I choose an element outside P, then this element has to be a factor of every element in P. Okay? This is exactly the definition of divided prime. So P, first thing you start with the prime ideal, we call it P. Whenever I choose an element outside P, then this element has to be a factor of every element in P. Okay. So look, and it's known that if this is true for every prime ideal, then R, we call it divided ring. So divided ring mean every prime ideal divided. Okay? And it is known that this class of rings are quasi-local, meaning they have only, each divided ring has exactly one maximal ideal. Okay, so here is a big class of let R be a divided ring. Then the two concepts are equivalent. Then I one absorbing primary if and only if I is a primary. Okay? So the answer to the question is wrong. No. What was the question? If you have a quasi-local, is it always one absorbing need not be one absorbing primary need not to be primary? No. And why? Here is a big clause. Here's the theorem. If you have a divided ring, then the ring will be quasi-local, but the two concepts are the same. Okay. Here is something as working on divided ring, a result observed. Let R be a divided ring with maximal ideal M. If M is not a principal prime ideal, well, we know every maximal is a prime. So here, if I know that the maximal ideal is not a principal ideal, what do I mean a principal? A principal mean the ideal will be generated by one element, like M equal XR for some non-unit X. This is a principal ideal. So here I said M is not a principal. That means M is not equal to XR for every non-unit X of R. Then look, what's the conclusion? Then every non-zero prime ideal of R also is not the principal. Wow. Okay, so if you have a divided ring, if the maximal ideal is not the principal, then none of the prime ideals will be principal. Okay? And here is another result related. like if you have divided integral domain, of course, all of you know what I mean with the integral domain. It means a commutative ring, but the only zero divisor of the rings is zero. So an integral domain is a commutative ring without zero element, except zero. And remember what zero element mean. Like when A is a zero divisor of R. If A times B equals zero for some B, for some non-zero B of the ring R. Anyway, so if you have a divided integral domain and P is a prime ideal, then P to the N is a primary. But I already proved in divided rings, there is no difference between one absorbing primary and primary. So B to the N will be always one absorbing primary. And the same thing. Okay, let me get to Dedekind domain or Bruffer domain. These are the classes I do with a Bruffer domain, meaning every finitely generated ideal is invertible. I think I mentioned the definition. Yeah. If you have an integral domain with a quotient field K, okay, and then a proper ideal I, we call it invertible ideal. If I times the inverse of I give you R. What do you mean with the inverse of an ideal? All the elements in the quotient field where Ri is a subset of R. Okay? R in K such that Ri in R. Ri in R. R, we call it a Bruffer domain if every non-zero finitely generated of R is invertible. That means I times the inverse of I will give you R. But this Bruffer domain for finitely generated ideal. Okay, since I mentioned Bruffer, maybe I should tell you what I mean with Dedekind domain. Dedekind domain, we remove finitely generated. So it become if every non-zero ideal of R is invertible. This is what we call Dedekind domain. Dedekind domain, we want every non-zero ideal to be invertible. Where a Bruffer, we want every non-zero finitely generated. Okay, here is a characterization. If you have a Bruffer domain, then these are equivalent. One absorbing always mean primary. Okay, so in a Bruffer domain also, there is no difference between the two things. This is theorem. The first one is kind of interesting. Why? You have a characterization of Dedekind domain in terms of one absorbing primary. Let R be Noetherian. What do I mean Noetherian? Every ideal is finitely generated. That's Noetherian. Then the following are equivalent. R is Dedekind domain. This condition is equivalent to 2. So in this theorem, we characterize Dedekind domain in terms of one absorbing primary ideal. This condition, these two are equivalent. And maybe one of the question you're going to ask me, wow, can I carry on the definition of one absorbing primary in terms of ideals? What do I mean with that? Remember, the definition of one absorbing primary has to do with the element. Whenever you have a product of three things in I, then you want, and these three things are non-unit, then you want A, B in I, or C radical of I. What about if I use the ideal? Like, look, for any proper ideals, I1, I2, I3, whenever you have a product of three ideals in I, then I1, I2 has to be in I, or I3 has to be a subset of the radical of I. So that means we can give the definition of one absorbing primary in terms of ideals, because the definition I gave you, it was in terms of element, but these two are equivalent. 1 and 2 are equivalent. Okay, one absorbing primary means that, and number 2 means that. Okay, I think I have maybe 5 minutes. How much time left for me?
Sir, just 5 more minutes, sir.
Oh, okay. So I finish up. I finish up with weekly. And what do I mean with weekly one absorbing? As you expect, when I add weekly, I still use the same definition as one absorbing primary, the same definition, but I add one more condition. I want AB not equal 0. So an ideal, we call it weakly one absorbing primary if whenever non-unit element A, B, C in R and A, B, and this, then A, B in I or C in the radical of I. Okay? And this is like related to weakly primary. Weakly primary, you just remember a primary and you add the condition A, B not equal 0. Okay? You see, read it. I give you a minute to read weakly primary and weakly one absorbing primary. Weakly one absorbing primary, the same definition as one absorbing primary, only we add the condition that ABC is not 0. Weakly primary is the same definition as primary, but we add the condition AB not equal 0. In fact, these definitions, they're inspired by weakly prime. D.D. Anderson and Smith in 2003, they introduced weakly prime. We know what it means. It means A, B in I, then A in I, or B in I. Weakly prime, we add the condition A, B not 0. So here I have N missing. If whenever you have A, B in R and A, B in I, then and A, B, then A in I or B in I. That's weakly prime. So all these weakly things, in fact, they were inspired by this paper in 2003. Okay, and we achieved some result on weekly, but I think you can read that on your own if you are interested. You see the difference between, I already gave you in details what I mean with one absorbing primary. So I think, you can finish up on your own when it comes to weekly. Yeah. Okay, I think that's a good time for me to stop. Hello? Hello? I think I finish here. So I stop, maybe.
Participants, if there is any query, please proceed. You can post the query in the chat section.
Okay, I have a question for you. Is this lecture recorded?
Yes, sir, it's recorded, sir.
It is streamed in
Will I-
YouTube also, sir. We have streaming in YouTube also, sir. Now people are watching. Besides the Google Meet, we are streaming live in YouTube also, sir.
I know, but my question, can I get a link for this lecture later
Yes,
on,
sir,
not now?
sure, sir, sure. I'll just send you your talk, sir. No issues.
Oh, okay, because I am interested in having my talk.
Yeah, I just send you the link, sir.
Thank you very much.
Thank you, sir. It's our pleasure, sir. Thank you.
Yeah, thank you. I hope one day, very soon, I will be in India.
So thank you, sir. Thank you so much.
Thank you.
Soon we would like to have you with us in India.
Yeah, I mean, I am a regular customer. I used to come to India 2, 3, 4 times a year. I hope soon we will start my trips to India. I hope so.
Thank you, sir. Thank you.
Thank you. Okay. So I can leave.
Thank you, sir. Your thought-provoking talk has set a perfect platform for the participants to intensify their knowledge. Thank you once again, sir. Thank you.
Thank you very much. I can go. Maybe I will come back later on.